Okay, awesome. All right, welcome everyone. This is the Variational Autoencoders Journal Club, or sorry, I2 Talks. We're rebranding. Keep forgetting. So this is the Variational Autoencoders I2 Talks. I gave this last year. I don't think anyone of you was here last year, so this won't be a repeat, which is nice. And I did some like small improvements to it overall. If anyone is watching the video, so this should be like a nice new version on this topic. So my plan in general is to just go over so variational autoencoders, that's two words. First, I'm going to go over what is an autoencoder, and then like why are variational ones cool, why is it useful, and like what can you do with it. And I also have an implementation of it online in case anyone wants to screw with it if you're familiar with PyTorch. So like, yeah, you don't have to build it from scratch. There's something online that you can mess with and experiment with new data sets. So just giving you a little taste of what's to come. So let's get started. So what is an autoencoder? Usually at this point, I'd ask like someone to raise their hand and like guess, but like I couldn't, like if I tried without knowing exactly what it was. It's not very intuitive as to what an autoencoder is. So, but don't be afraid. The word, it's not a crazy concept, especially if you know what a neural network is. So just like show of hands, who here knows like the general idea of like what a neural network is? Wonderful. That's totally fine. Not even like deep knowledge, but like if I showed you a photo like this, could you ID this as like a neural network, right? And if you can't, this is what a neural network looks like. Don't worry about all the notation inside the circles. This is just the image I found online. But the general idea of like what a neural network can do, you take the vectorized inputs, which is x1, x2, x3, and x4. It gets multiplied by a bunch of matrices and transformed into vectors of different sizes. As you can see, this one goes from 4 to 3 to 4 to 2. Not really a good architecture. It's just useful for showing it off. And the final like output layer right there, y1 and y2, is usually either a classified or regressed output. What that means is if it's classification, this would be a binary classification task in the sense that this would probably output a probability that whatever you inputted it in was in class 1 or class 2. Say I gave it like a dog, features of a dog, for example, and dog was like the first class, then we would hope that this trained neural network would output like 1 on y1, like the output y1 would equal 1, and then y2 would be 0. But if I give it a cat, it should hopefully accurately classify this as this image as a cat by giving me y2 equals 1 and y1 equals 0. Basically, you have inputs to the network, and then you have some goal of the network to either classify a bunch of objects, or when I say regress, I mean basically guess some discrete value in between, like, sorry, not discrete, continuous value in between. Like, let's say you give it the dimensions of a house and you guess the housing price. That'd be regression, right? Because it can have any like reasonable number. That'd be regression, right? So that's generally what neural networks can do, along with a lot more. You can check out the Deep Learning Neural Networks lecture on the I2 YouTube if you're interested in more. But yeah, anyway, just to get on the same page with that, this is what a neural network is. Now, an autoencoder is legitimately just a neural network that has a little more like constraints on it in terms of its shape. So it's legitimately just a deep neural network that is characterized by, like most of the time, this does not make absolute statements, equal input and output dimensions. As in, the final layer of the network is the exact same dimensionality as the input layer. And this is critical for a reason I'll get into right after this. The second thing that an autoencoder generally has is a bottleneck layer, which is to say a layer usually sandwiched right in between all the other ones that is small. And small is relative based on the input size, obviously, but it is generally a good deal smaller than whatever the dimensionality of the input is. In this case, you see like 6 inputs and then you have like 3 in the middle bottleneck. That's going to cut the dimensionality in half. And that again becomes useful for a reason I'll get into later. And finally is they operate on this idea or training method called self-supervision. And I'll get into that again in the next slide. So I just want to make sure everyone's on the same page, that an autoencoder isn't something necessarily crazy. It's not some insane like architecture. It's legitimately just a neural network structured in a certain way. So any general questions on that so far before we really dive into it? All right, okay. So the last bullet point there was self-supervision. And I want to get into what exactly that is. So this is a little more intuitive as to what self-supervision is, essentially. So if you did the deep learning unit, you'll know that we did something called supervised learning, in which there is an image, like let's say the digit 7, and that digit 7 will have like a label associated with it, right? So we'll have like, here's a picture of a 7, and then somewhere else in the code paired with this in some, understandable way, there will be like an integer 7 or something of the sort that is a way to tell the neural network what the label of this is. Because we can tell this is a 7. To the neural network, it's just a set of pixels. But the neural network can understand in certain ways what this integer 7 is, right? So that would be supervised learning. Self-supervised learning happens when you just have like the photo. Like, let's do like all I give it is this. There's nothing else. There's no label to it, right? And you might be thinking, okay, well, how exactly can a neural network learn if there's no ground truth? That's what these things base off of, You pass it in some image and you tell it what that image is, and then it back propagates to update its weights such that it can now classify or understand that image better. And then you iterate until you reach a local minima, and then you're good. You have a trained network. This is a little different. So usually, we'll have all these labels and stuff like that, but that can be hard to get. Especially you can think about like complex images, right? Say I took a photo of this scene right here, and I gave it to someone to like annotate. Like there's a lot to write. There's trees outside. There's a bunch of people here. The tables are whiteboards that you can write on. Pretty cool stuff. A bunch of green chairs. Like, oh, is that UW? Like, it's hard to get that information, right? But taking the photo itself is not that hard. So you can see the leap in, like, I guess, not complexity necessarily, like difficulty in acquiring a self-supervised data set versus a supervised data set. Getting a supervised data set requires labeling all your data. For self-supervision, when you hear that a model is self-supervised or learns through self-supervision, that means that you generally don't need labels, which means that you can have a lot more data that's easy to collect, and you could be more intentional about debiasing it, right? Oh yeah, whoops, forgot I had that there. So that's like the official definition of self-supervision. You can take a second to digest that if you'd like. But in general, you could call it just like the idea that there is no label, but learning can still happen through some pretty cool and clever tricks that we have. For an autoencoder, what that means is essentially, remember how the input and output layers are the exact same size? That means your input can also be your target, which you might think of, why is it useful for a network to take data and spit out the same data and not make a classification or regression, right? Well, you'll see why that becomes useful in a little bit, but just know that like we don't need labels to do this kind of stuff. You pass in this digit 4, and you are hoping to get that digit 4 on the way out, right? And just as a quick note, just because something is self-supervised doesn't mean it is unbiased. You can still have bias in a data set that is unsupervised. For example, not having much of a certain class or classification that you need. Not having enough of that will still heavily bias the model, even if there are no labels. So just keep that in mind. Just because it's self-supervised doesn't mean it can't be a biased model. So one application you can think of when it comes to like self-supervised learning and autoencoders, right? Say we have an image. That's our original 7. We can algorithmically add noise to it. That is something that we can do. You can do it in code. Just literally add random white pixels, right? And now you have 2 images, one of them being the input and the other one being the output. So what you've created here is basically a denoiser if you train it on this data, right? You pass in a bunch of like crappy images that you generate from good images. And now you have 2 images, one of them being the input and one of them being the output. And now you train it on a bunch of different things, make sure it sees like a wide swath of pictures and characters, and then you can give it like a really crappy low-res image, and all of a sudden you get on the other side a new upscaled image, right? So like, I'm not saying that all image upscalers work this way, but I'm sure a good portion of them do, employing an autoencoder in some way so that you can essentially denoise the input data. And you can see how this is super powerful. Like, if you take a look at there'll be a notebook at the end that you can mess with this. If you create just a very simple method that takes in like a grid of pixels and noises it, you can make a denoiser on your computer for like if you want to test it out on your own images, right? So you take a really blurry photo. Well, if you have a bunch of data of very blurry photos and their clear counterpart, perhaps you can train a model that can de-blur your photos for you. Pretty cool stuff, right? And this is just a normal autoencoder, and this is what it can do. It's really just an application of neural networks, which again are wonderful. But I'll get into like how we can use this for even cooler stuff, as you can see. So one thing that I'm going to jump into now that we actually pause. Any questions on the idea of an autoencoder? The general idea. Okay, wonderful. So now I'm going to go over a very important concept, not just to variational autoencoders and autoencoders, but to deep learning in general, which is the idea of latent space. So this is the same image I showed you before, zoomed in a little bit, and you can see that there's like that bottleneck right there, right? So I think, what is the next slide here? Just make sure. Okay, yeah. So I'll go over like a high level idea of this. As I noted, the input was very high dimensional. The bottleneck layer is, by definition, smaller than the input space, right? And halfway through the network, right, before it gets decoded on the right-hand side, as you can see there, it gets encoded. You take the input, you matrix multiply it, and slowly send it to this smaller dimensional space. Like this image right here, MNIST is 28 by 28, so 784 dimensional points, essentially, right? This could be 2. You could send this MNIST image and represent it in 2 dimensions, right? And then the network's job is to take that and blow it out back into 784 dimensions again. And then you can reshape it into an image, right? So that's just like the idea of what a latent space is. A latent space is basically a collection of these points that exist. Sorry, make sure your heads aren't in there. I think you should be fine, but yeah. The latent space is this thing in the middle when it comes to variational autoencoders. Essentially, where these compressed representations of data lie, okay? So you can consider that like, say I take a high resolution image and then I compress it, and the high resolution image was 1,000 by 1,000, but the smaller one is like 100 by 100, that all those smaller images live in this latent space of 100 times 100, right? Dimensionality. Is that like somewhat clear as like what a latent space is? It is essentially like a lower space in which lower dimensional data is represented in the context of there being some higher dimensional representation. Yeah.
Why does it need to do the low dimensional thing when at the end it's gonna be high dimensional?
Yeah, that's a good question. So actually, I'll go into the next slide and that should answer that, right? So why does it necessarily, why is an autoencoder useful if all we do is recreate the input image, right? So remember this, the bottleneck exists. The data must flow through the bottleneck to get to the other side, right? And also, if you go back to here, you can see that, kind of ignoring this first green part right there, just take a look at what the network's doing from here. It's taking what I said could be 2 dimensions and blowing it back out to 784, right? That's not an easy task. Like from the points 1 and 7.93 or something like that, right? That's all this network has. And all of a sudden has to recreate this without some explicit mapping being given to it, right? That's a difficult problem. And the reason, and by training a network to do that, there's some pretty cool things that can happen and consequences of that. So the main idea is autoencoders can take high dimensional data and turn it into low dimensional data, right? And from this low dimensional data, they can also recreate that high dimensional data, right? They're not referencing that original thing and being like, oh, let me just spit it out again. It can't do that. You're not letting it see the original input. Basically, it's just taking it in, compressing it, and then blowing it out again, right? So from this low dimensional data, 2 points, like X and Y, it can create an image, a 784 dimensional image. So therefore, the representations in the latent space are somewhat accurate, but really, really, really heavily compressed representations of the input data. And that's why it's crucial. We have found a way to represent the digit 7 in 2 numbers through this autoencoder, which is really incredible. And based on how well the autoencoder does at this compression, it can recreate the images with like relatively good fidelity. which is again cool because basically if you cut off the encoder part of the autoencoder and just use the decoder, you can feed it some points that you know would generate sevens, and it'll make sevens for you out of 2 points, right? Which is pretty cool. You can think about that. Like, how else necessarily would you go about that? Compressing the digit 7 and all of its other variants in a data set into 2 points, right? So, yeah, that's what the neural network can do, right? Y'all have any questions? None at all? Wow, y'all are crazy smart then. Yeah. So yeah, before I move on from this little slide over here, any general questions on like why is this framework useful?
This isn't necessarily about why it's useful, but when it outputs the ending data, will it be like, so let's say when you input a bunch of different of sevens in different handwritings.
Mhm.
Will the output seven be like one of the specific handwritings, or will it be like kind of like a combination of all of them? Or?
So it's you feed in one image at a time, right? So like say you have a 7 written really thickly or something like that. The hope is that it should recreate the thick 7, right? And then, say like I write a really thin 7 or something like that. That where the goal of the network is to output a really thin 7. Now, if you say, hey network, generate me a general 7, then it should give you some kind of averaging of all that, right? If it sees a lot of thick ones, it'll hopefully spit out a thick one. If most of them were thin, only one of them was thick, then it'll spit out a thin one, right? So like the answer is like if you're asking it to generate something, it'll be an average of all of them or like a general like aggregation. But if you're doing like a one-to-one, the goal will be whatever the input is, right? Did that answer your question?
Okay, so the autoencoder is trained on matching the input to the output instead
Yes.
of like putting in a bunch of data.
Yeah, so you want to take the input, compress it, and get the same input, right? Any other questions? So if I don't answer your question, feel free to just say it over and over and over again until I do, because I really don't mind that.
So, is there any actual use of the image, like the bottleneck image that we get for anything?
Yeah, so it won't be an image. It'll be like some data, like two numbers or something, right? But there is a ton of uses for it. In fact, I would argue that creating that space and a decoder for it is the main purpose of the autoencoder. And I'll get into like why it's useful. Any questions other than that? Okay, cool. So let's get a little more abstract here, right? Move away from MNIST. Let's say we are describing a dog, a bird, a car, and a plane, right? There's a lot of features to this. Maybe the number of wheels it has, can it fly, is it alive, things like that. So if you were to plot a dog, bird, car, and plane, can someone tell me like how would you plot these in a way such that it's understandable, not knowing what they are? You could show it to someone else and be like, this is relatively more insert characteristic than this other one. What are some ways you could do that? Like, yeah, maybe like the more green it is, like the more alive it is, right? But then how would you distinguish between a dog and a bird? Like they're both equally as alive, right? And then all of a sudden you lose some information there. A dog and a bird are the same thing. Anything else?
You can do in the sense of numbers, like if like they get fly, that's number one,
Mhm.
and if you add at the end, if you end up adding them all up,
Mm.
you can see how it is really together.
Yeah, that's a really good idea. Now, like, let's say, for example, I put a jetpack on a dog and all of a sudden it can fly, right? Then that dog all of a sudden gives you like a new output number that isn't in any of the other ones. So like new data would mess up that schema, right? But right. So let's look at a bad one first. We'll put them on a line of living. This is kind of what you're thinking about, right? All of a sudden, the distinction between a car and a plane, like how is a plane more alive than a car? Like no real reasoning to that. This is the best you can get with one dimension, right? With 2 dimensions, it kind of makes more sense. You can kind of put them on like, do they fly and do they live? And then each one exists in a certain quadrant, right? So wonderful, we found a way to take our data and encode it into a 2-dimensional space such that the information that is important is kept, right? We did this manually. Autoencoders do it through backpropagation, right? Now, here's kind of where we get into the variational stuff. Wait. Oh yeah, hold on. Sorry. Let's see. So, what if we selected, you can kind of ignore the top text here, just listen to what I'm saying. What if we selected a point right there? Like a new point. Like we know where these points exist. You know, that's like 3, 3, 3, -3, whatever. But I chose like 0, -3 or something like that. Something that nothing else gets to. Well, what we would hope is that we would get something that is, you know, not living, but can somewhat fly, but also doesn't always need to, like a car-plane hybrid. That's what that point means. That's what it's in telling us. Like if I pull something there and I draw a little image, it should be a car-plane hybrid. But the reality is that if we were to do that with an autoencoder, it would give us like random noise. And there's a reason for that. Standard autoencoders are not motivated to create new things. There's no reason that, you know, you give it a bunch of 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and 9s. It doesn't need to create something between an 8 and a 9. It can just say, okay, all zeros, let's call them 1, 1. All 10s, or sorry, all 9s, let's go to like -7, 3. Like basically, you'll have a grid. I hope you guys can see this, by the way. Like you have a little grid, right? Let's say we're compressing the 2 dimensions, and then all the like zeros will exist here. All of like the 7s will exist here. All of like the 3s will exist here. And this stuff in the middle is like nothing. There's no smush between like a 3 and a 7. There's nothing special that comes out of there. But wouldn't it be cool if I could say, give me a new number that like looks like a 0 and a 1 at the same time? Like I don't know what that would be. But I'm just the idea, like I use numbers here, but the idea is, say you had more like ideas or like pictures, right? Maybe you could generate something like, say you embed a photo of like a king and a woman, and maybe in between them you get a queen, something like that, right? That'd be pretty cool. Unfortunately, like I said, standard autoencoders encode stuff like this, where everything is very discrete and it's not useful to interpolate between them. So, oh, shit. Big quote again. Sorry, there's a lot of text on this. But the core of it is the part I bolded. Autoencoder is solely trained to encode and decode with as few loss as possible. Essentially, what is the best way that I can map things to points, and then understand that and decode them. And the most efficient way is really just to assign them discretely. Like, why would you want to waste your energy and optimization on trying to create new things in between? You're not really motivating for that. So that's why a standard autoencoder cannot generate things in between things it's already seen, right? It's useful for denoising, as I said, but you can't generate new things, and wouldn't that be cool? So yeah. Any questions on like why it's not able to do that? Like just conceptual questions too. I'm totally open to whatever. Yes.
Like if there's an image which is like apparently very very perfect,
Mm-hmm.
like it can't be very. Is there a chance that it would end up becoming something different because it's so heavy?
Yes. Yeah. It would probably like if you train it on ones, like I said, if you train it on the digits, then all of a sudden I give it like a picture of a dog, it's going to end up in nonsense space, right? But it's also not going to be able to decode the picture of the dog. So you can't just feed it the picture of the dog, look at where it is, and then feed that point and spit it out. It's going to just spit out like noise, basically. Unfortunately, it can't like immediately adapt to a dog. Yeah, it'll like create like just a blank screen or something like that. Not very useful. Anything else? Be honest, is everyone following me so far? Hell yeah. Somewhat? Good. And if there's any questions, please just like interrupt me and I will answer them. So now we've talked about autoencoders and their drawbacks and the problem we're trying to solve, I will introduce the concept of a variational autoencoder. This is where I lose people, so please ask questions. So what do I mean when I say variational autoencoder? So when I say variational autoencoder, we want something like this. where we train it on like triangles, squares, and trapezoids, triangles, squares, trapezoids, and circles. But in between, we can actually get like new shapes. Like, oh, what's in between like a square and a circle? Like maybe a squoval or something like that, right? Or you have like a trapezoid, and you're kind of getting towards like this is the circle's space, right? And this is the triangle's space. In between them, you get this little thing, right? That's our goal. A variational autoencoder should be able to do this. The latent space, and hopefully you understand what I mean by that. The latent space is smooth. You move through it, you get useful, cool things, not just a bunch of noise, and then you get towards the center of a cluster, and then you start getting digits, right? You want it to actually be useful all the way through. So this is the goal. This is what we're like working towards, and this is what we want to motivate our autoencoder to embed like, right? Because our autoencoder does the embedding for us. And when I say embedding, I mean taking the high dimensional image and turning it into a point in the latent space. That's what when people say embedding, that's what they mean. But we want to make it so that the embedding space, aka latent space, is smooth and useful. Does that make sense? Okay, great. So how we do that is pretty cool, and it does require a little bit of statistics knowledge, but not too much. So instead of the bottleneck representing a single point or a vector in some dimensional space, right? I've been using 2 as an example, right? Instead, a variational autoencoder encodes input as a distribution. And what that means is, if you've seen distributions before, maybe you've seen like a normal one notated like n, mu, comma, sigma, something like that. Essentially what that tells you is like the mean and then also like the standard deviation of a Gaussian curve. And that is what this represents essentially. It's spitting out a mean vector, which is going to be a list of mu's, like mu1, mu2, mu3, and a standard deviation vector, which each one pairs up with one of the mu's. So standard deviation 1, like sigma 1, sigma 2, sigma 3, and so on and so forth. And what that does is lets us sample from that distribution, and then you'll get a latent vector. And the thing about sampling is it's an inherently stochastic process. So I could have this distribution, and one time I could sample and I could get this point, the next time I can sample and get this point, or then this point or this point. So it's not like the same image is going to end up at the same point each time. The same image might encode very similar means and standard deviations, but that doesn't mean that they're going to end up in the same spot for the decoder to try and work with. What this means is that the decoder will see a lot of different points that all mean the same thing. So we've gone from taking like an image of a 7, right? And then it being represented as like a single point on a grid. What instead we have now is that this 7 is kind of in a cloud. So it's like it sometimes ends up here, sometimes, and the decoder has to be like, okay, everything in this wavy bubble is going to need to look like a 7. And everything in this wavy bubble is going to need to look like a 3. And now you can see they kind of cross in the middle there, and that's where we hope to get that generation. Because now, in that space, sometimes 3s pop up, and sometimes 7s pop up. And what do you get when you have, like, sometimes it's being trained on a 3, and sometimes it's being trained on a 7? You get a combination of the two, just by nature of how gradient descent works. Because sometimes it'll backpropagate and optimize for a 7, and sometimes it'll backpropagate and optimize for a 3. And then those weights will be added up, and then you'll be able to generate something between a 7 and a 3. And this is in case it didn't make full sense, like how is there a mean vector and a standard deviation vector isn't a distribution represented by one mean and one standard deviation? Well, this two-dimensional example should hopefully have it make sense. If we had a vector of 2 means and 2 standard deviations, you can consider like a 3D plot that would look like this, right? This is how you can take a vector, technically 2 points is a vector, right, of means and standard deviations, and create this plot. Now, we'd be doing this in like 64-dimensional space, which is impossible to visualize. But the idea is that essentially each axis is going to be dependent on one of the distribution parameters, meaning the mean and standard deviation. Any questions on that so far? Okay. So here is the problem, right? If we force this to happen by, well, adding that thing I was talking about, which is the mean and standard deviation vector, just putting that into the architecture, we do enforce something called local continuity, which means like, oh, around the area of a 7, you will generate 7s in the latent space. Like, let's say, like I said, that bubble over there generates 7s. Then like I could sample anywhere in that bubble and I'll get something that looks like a 7. We have that so far, right? So we've kind of solved one part of the problem, which is making sure that the representations aren't too discrete. They're not too closed in and dense, right? The problem is, though, we don't have global continuity, which means that the network can basically cheat, and it does. Basically, it's like, oh yeah, I can make a bubble here, I'm also going to make a bubble here, and here, and here, and they're not going to touch. And then you're back to the same problem with bigger circles, right? So they're all over the place. There's no motivation for them to touch, so it's not going to, right? So if you have very low standard deviations and very distant means, you essentially create discrete points again. And you don't want that because we were just trying to avoid that, right? So we can solve both of these problems by modifying the loss function of a network. Now, is anyone not familiar what a loss function is? Yeah. So a loss function, in terms of deep learning, is essentially a way to say, okay, here was the prediction that you neural network outputted, and here's what you were supposed to output. A loss function compares the two and tells the neural network how good or bad it did. Usually, a high loss means it did really bad, right? Say it was supposed to generate like a 7, and it spits out like something, like a bunch of white pixels or something, right? The difference between an image of a 7 and a bunch of white pixels is easily quantifiable. Just subtract the two maybe and sum up all the differences, and you'll see that the network will notice that, oh, I did really bad on this one. Let me update my parameters so that next time I see a 7, I don't do as bad, right? That's what a loss function is. And if a note is that basically, if you don't clearly optimize for something within the loss function, if there's not something in the loss function telling the network to make yourself have local and global continuity, for example, it's not going to do it. There's no reason it needs to be, right? So we need to tell the network what is good and what is bad. Like, what do you want to optimize for? And just in general, if you're like, why isn't my network doing X? It makes complete sense. Like, the autoencoder, why doesn't it just make new things in the space in between? Because you didn't tell it to. And more often than not, it'll find out a way to do things that doesn't have these nice downstream consequences unless you explicitly optimize for them. So if you're ever trying to build networks in the future and you're like, oh, my network is like overfitting heavily. Well, did you add a regularization term that penalizes overfitting? If you didn't, well, your network's going to overfit because it can, right? So how do we make it so that all of these things are together in one space, right? Like, how do we make it so that, oh, I want all the bubbles to be concentrated around the middle? Like, I want one bubble here, one bubble here, one bubble here, and one bubble here, right? Well, the answer is kind of what I drew out right here. What we can do is also penalize the network if it creates distributions that are very far from a standard Gaussian, which is mean 0, standard deviation 1. So now the network has to do two things. It has to actually make like a bubble in which samplings will result in something useful, and that bubble must be centered at 0 with a standard deviation of 1. So the bubbles are now of even size and at the same place. But you can't have them all overlap or that won't make sense. So it's almost like they're kind of squishing together around 0, 0, trying to compete for who can be at the center the most. And then boom, you have something like this, where they're all kind of squished together and you get cool things in the center, like a combination between a square, circle, and triangle, which that's pretty cool. So that's how we do it. Now, how do we actually penalize for being far away from a standard Gaussian? I just said that. So you calculate something called a Kullback-Leibler divergence. Can't say that. Basically, what it does, and it's a fancy name, it finds, and you can just call it KL divergence, but it finds out how different two distributions are. right? So you can take a look at what the standard Gaussian is and like what different means and standard deviations will do to a distribution. And we're trying to basically say, all right, you're going to give me all this wacky means and standard deviations. We're going to force you to try and be mean 0, standard deviation 1. And the farther you are from that, the more we're going to penalize you. That's the idea. And now we've kind of solved the problem. We've made it so that there's bubbles being created, so it's not discrete sampling. And we've also made it so that all those bubbles center around 0, 0, or what would be 0, 0 in high-dimensional space. Now, whenever you sample from anywhere around that's like origin, you'll get something unique because all these bubbles are like colliding and clashing, and you'll sample something in between them and you'll actually make something new. So this right here is a loss function, essentially. I'll go over each one of these like items, and you can take a look at them on the left if I'm talking too slow. This is the original input, so that'd be the 7. This is what the network gave you from the reconstruction. You can just subtract those and square it. That is MSE, loss. That's what we had originally. Basically, just can you reconstruct the input. Now we're going to add this KL divergence term, which is, okay, we have the parameters of our distribution that the network gave us, which is from the middle of the model. Remember, because we have the architecture, create a mean vector and a standard deviation vector. This is where that mean vector will go, and this is where that standard deviation vector will go. And then you will compare that to a standard Gaussian, which is 0, 1. And then this will give you a number, this will give you a number. You sum them up, and the higher that is, the worse the network does. And then the network will try and optimize for that and create that nice, smooth latent space that we've been going after. Anyone have any questions so far? Yes. So you have to be smart about it, right? Like variational autoencoders, they are a type of generative model. You obviously, like, neural networks are really powerful. So they could probably deal with a lot of things, but you would have to make a really big network trained on GPU. It would probably be able to pick out a lot of patterns, like say you give it dogs, cats, and a bunch of other animals. Maybe it'll make something nice, but like only recently have generative models not spit out amalgamations of flesh. I think some of you might know what I'm talking about, right? Like maybe 5 years ago, the best the generative model could do was like some horror face, like some creepy shit, right? So they've gotten a lot better at that. So it's a recent addition. This variational autoencoder stuff is like mid-late 2010s type deal. So we've not moved past this because it's super cool, but like this is definitely not what's going to give you the high fidelity images that you see today in generative models. Yeah. So we're not done yet. Please stay awake. Okay, so here's some more intuition and math on like, what time is it? Oh, huh? Okay, I got time. So some of you who may know a little bit more about how backprop works might know that you cannot backpropagate through sampling because that is non-differentiable. The way that they get around that is essentially through a reparameterization trick. I won't go into it because this is more a slide I have. Goodbye. This is more a slide I have if someone like, wait, sir, what about this thing, right? Then I show them this slide. I'm like, okay, pipe down. So does anyone necessarily want to hear about the reparameterization trick and how it works in backpropagation? Yeah, I'll give like the TLDR. Essentially, like I said, if you're generating mean and standard deviation vectors and you sample from them, you cannot backpropagate to that. Gradients kind of stop there because they're like, okay, you've sampled randomly. I can't backpropagate through that randomness. That's just a fact. Backpropagation only works on fully differentiable equations. And once you sample, that's not differentiable. Like, what's the derivative of the normal, like a normal distribution sample? It's not. It doesn't make any sense. So the idea is instead, you basically have the network like, in a sense, like, where is it right here? Let's see if I can point it out. You have it so that instead of like explicitly sampling from the distributions, it basically takes the numbers that it spits out and then just throws it into a differentiable equation that approximates a Gaussian, right? And then that's differentiable versus like actually doing stochastic sampling, right? So for example, you can see right here, this Z output, you can't backpropagate up to this normal distribution that's right here, but you can backpropagate through the mean vector and the standard deviation vector if you have it so that this thing, which is, you can't backpropagate through it, is, see that right there? Like a variable that you multiply by. So you sample from a normal distribution, right? Like a standard normal distribution, and then you multiply or scale it by what you spit out here. And that's just a multiplication. So you can backpropagate through that. So you move the sampling over here, where it basically doesn't screw with the backpropagation. It's a little interesting. You can see like this, I don't know what the hell that Greek symbol is, but that represents like some vector of samples from here. And then you just scale that by the mean and standard deviation. And then now you have essentially sampled without actually sampling. You sample, but it's in like a different like leg of the computational graph. So, and also if you care about the KL divergence equation in code and like what it looks like for discrete PDFs and continuous PDFs, this is what it is. It's not crazy. It's basically just like log prob of like each of the discrete elements, or you integrate over it, and you multiply that by the probability of one of them existing. I don't know if you can see that. Right over here. This might be understandable if you know Python, but it's literally just like for every single element in A, or like you take it, multiply it by the log of that element over its equivalent in B. That's it. So you can take a second to digest that. And that'll give you like a single number that tells you how far apart these distributions are, which will be useful in our loss computation. Any questions on that? Okay. Sorry, question? Okay. All right, so now that we've gone over the difference between a standard and a variational autoencoder, let's go over some of their benefits and drawbacks, because obviously I don't expect everyone to immediately absorb what this is and go make one themselves. Just you should know the differences, so if you do ever decide to do that, you can look it up and understand why you'd want to use one over the other. So a standard variational autoencoder, they can both encode into latent space. They can both reconstruct the latent space. Standard ones can denoise better right out of the box. I've found through my experience, variational autoencoders can be kind of unstable. They're also more lightweight. Sorry, I found that standard autoencoders are more stable and they can be trained quicker and they're more lightweight because you don't have to deal with all the reparameterization stuff. It's also way easier to implement a standard autoencoder over a variational one. You cannot reconstruct proximal points in space when it comes to a standard autoencoder, and you can't get the standard autoencoder to generate stuff. It's just not meant to be. Variational one, basically, you're trading off a little bit more complexity for a little bit more ability, which is how it tends to be in deep learning, right? So you can denoise with some modifications to the architecture, so it can still do everything a standard autoencoder can do, but it's not going to be as lightweight. Like you'll need to do a little more manual engineering and such to get it to behave the way you want. So those are the comparisons. I can hang around on the slide for a little bit, also if anyone has any questions. I'll also post these so you can reference them later if anyone needs to. Well, no, I'm sure there's a bunch more. Let me see if I can think of any. Denoising, but also like removal of some item, if that makes sense. Like if you say you have something that, say you have a bunch of training data, right, that you can somehow have like something's in the picture and now something's not. You can essentially train the autoencoder to transform any image to having that to not having it. Like for example, you can have a bunch of photos of people with and without their mustaches, and with some training tricks, an autoencoder can learn to take someone's mustache off, right? It's pretty cool. Yeah, there's more reasons. More applications. I can't really think of them right now, but they're still very useful. So like, if you're interested, you should definitely look it up later. Anything else?
When you read the bubbles with the axis, you can make the true matching with the
So people like the standard normal distribution, which is mean zero, variance one, because well, it's just well known, it's clean, it's easy to calculate stuff off of. I mean, if you were to change the mean of like basically you're optimizing for the distributions that the autoencoder generates to be like the one like if I replace this with something else, all these things would start trying to shift over there. Like maybe I put something like, oh, now, haha, you're gonna be trying to generate at like mean 4, standard deviation 10 or something like that, right? Then all these bubbles would start migrating over here. I don't think you would like. There's no necessarily like a reason to. It would, if anything, it would just be slightly worse. I think. I have never tested it myself. You could test it with the implementation I have and see if it does. But to my understanding, like I don't think it being a standard normal is like required for this whole thing to work. It's just the best choice. Like any other choice would seem arbitrary. So, anything else? Yeah, you could probably actually increase the variance of. You also run the risk of like the sampling being so stochastic and so spread out that the autoencoder doesn't really make sense of this big kind of like bubble that's being generated. But I'm sure by increasing the variance of like the variance of the distribution in the second part of the Kolbach-Labor divergence equation, you could try and expand the bubbles a little bit. Oop. Anything else? So here's some cool stuff you can do. Here are some combinations of emojis. I'm not saying these were created. Yeah. Yeah. I'm not saying that these were generated by a variational autoencoder. I have no idea. My friend spammed me with this one at one time, and I was like worried for him. So I don't know. These are crazy. I don't know. I laugh whenever I see these. But you're asking for applications, right, of autoencoders? Denoising, you have dimensionality reduction with clustering and classification, content generation, like it's over here. Feature detection and anomaly detection as well. Yeah. So, and also like maybe now if you can program in Python, like maybe you're thinking of some ways to integrate this into any projects you have. It's not really hard to get this up and going in Python, and there's plenty of implementations out there for PyTorch. So yeah, can anyone throw out like maybe a use they could see for this cool stuff? Mm-hmm. Yeah. You'd probably need a lot. Like these are way too clean in my opinion to be like generated by like what would be a standard variational autoencoder. I'm sure there were some tricks. Like I mean, the thing that makes me think that these were somewhat programmatically generated was that one. Like, are the people at Android like really that unhinged? Like I don't know, right? But so that made me think that there's some programmatic stuff going into here. Maybe for the less known combinations, like they did that. But like those ones are way too nice. So I wouldn't expect those to be generated through a variational autoencoder. Or like if you were to oh yeah, because there is a stochastic element to the basically the decoding, which is if you look over here in the reparameterization, this is stochastic. It'll sample from a normal distribution. If you set some random seed and locked it, it would probably be the same each time. But yeah, with a standard variational autoencoder, it'll be a little random each time, even if you give it the same point because of that sampling. Yeah, here are some more. Thought these were funny. Like this one is ridiculous. Like I don't know what's going on over here. This one, Jesus Christ. Serious? These are pretty funny. So yeah, and, like some of them are interesting. Like this one looks like something went wrong, you know. So this is why like when my friend sent me these, I was like, is there something up with like how they're generating them? I don't know. Maybe someone can look into this and let me know later. I haven't had the time, but yeah. So in case I spoke too fast, which I don't think I did. What time is it?
It's 5 minutes.
Oh, wonderful. Okay, good. Last time this took like wait, I think it took way too long actually. I did not. I spoke really slowly. But yeah, these are two videos that you can see. Like this is basically like how I learned about them, and some other like just general research. These videos are great, so I'm gonna post the slides later, and then if y'all are more interested, like definitely watch these videos. They're really good, especially if you need a refresh on anything I said. So yeah. So now, really quickly, I'm going to go over an implementation that I made a little bit ago for a class. This is like right here. I trained it on MNIST, by the way, which is just a collection of digits. That's what I was like kind of showing over here. And I did basically what I said I would do in the presentation. And this is essentially just a grid. I think somewhere here is like centered around 0, 0. And you can see like in certain directions you get like ones. In certain directions you'll get like in certain areas you get like nines. You know, I was iterating on integers, so it's going to be like a little less smooth. But like you can kind of see how stuff up here is like the 0 area. Here's like gets into nines, and it gets more into ones here. There's like clouds kind of combining. This is like the one cloud over here. That's like the 0 and whatever else cloud over there. This is like there's an 8 right. I don't know what's going on over there, and there's some other stuff here. Like, and the center is kind of like around here, so you can see like the collision of those clouds in this image, which I think is pretty cool. So I'm going to switch over to the Colab now. Oh wait, I think I'd run it earlier. Oh no! Oh shit. Here, this one maybe is a little more clear, but like you can see, like more clear nines, for example. Maybe the ones ended up there this time because again it's stochastic. But this is a minimal implementation of a variational autoencoder, and the code needed to like run and analyze it. Oh, it's all the reconstructions. Oh, and you can see like when it started out, this is what a reconstruction was over a batch, and it slowly gets like a little bit better and better. Like it struggles on some stuff here. I think it just like, yeah, it kind of shits itself when it sees threes, but yeah, that's and also sevens, but yeah. So you can kind of see how this is going, and like this is pretty cool to see it in action, right? And the code itself, just the PyTorch, like just this cell is the entire variational autoencoder, which realistically is not like an insane amount for PyTorch code. So like, and you can see right here, like explicitly where I calculate the KL divergence loss. You can experiment with the variation as well. Like I don't know where I put that exactly. I have to look at that. But yeah. Also, like if you ever get stuck, there's always stuff online. Hopefully this like because all the stuff online, I don't know why, but they're always doing something a little more complicated. So this minimal example should have just like, well, the bare minimum to use a variational autoencoder. So yeah. Here are the resources that I had used to make this like from a while ago. If you want to dig deeper into it and check things out, like these are really useful. So like check these out when you get the chance. And yeah, that's all. Thank you. Cool. All right. I'll take more questions, but let me just stop the recording real quick.